honestly forgot about it until like not
Well, I just
It'd be kind of funny if I prematurely put my exams into the share folder. Or put one there, except it's intentionally put there just to see whether people want it. Yep. Question?
Yeah.
Yeah. Huh?
So for the lab, the one where the C code for?
Yeah. I can't hear you, sorry.
Okay. You got the right code, right?
Uh-huh.
Ever since class. And I did the copy for the drive. Like when you have to put your student ID.
Uh-huh.
And I'm trying to remember, but I don't think it worked. I
You
did
have
turn in
to-
the one. I made a copy to my drive and I edited that.
Uh-huh.
And don't think it. I think it had the same number on there, so I took that number, like the same one you originally had.
Yeah.
I think mine didn't change. That's why I just put that number.
What happens when you try to change?
When I tried to change it?
Yeah.
It just left the same number on mine. But
Okay.
now he's trying at the dude next to me is trying it. And I was
Uh-huh.
like, wait, why'd yours number change?
Yeah.
Yeah, mine didn't do that. But
So
I have
that
the
means-
right code if you want to see my code.
Well, you're in the late lab, so it's due tonight, not yet.
Okay, so I can do
Yeah.
it.
Alrighty, it's 7:01, so I'm gonna start the lecture. So we're gonna look at the exam questions again. If you're from the late lab, this might be an overlap with last Thursday because you guys might have seen the solution already. But the early lab has not seen it yet, and this is also being recorded. So we're gonna go through this first, and then we'll go into the go back to memory devices today. All right, so this would be a good time to ask questions if you have any issues with the exam 1 questions. If you need clarifications or if you want to suggest a different way of asking a question, now would be a good time to do it. All right, so question 1 is, consider a binary subtraction involving a 3-bit minuend and a 3-bit subtrahend. Step 1 is just a yes or no. Is it possible for the overall borrow to be set, which means it's a 1, and for the sign flag to be cleared, which means it's a 0, after the subtraction? The answer is yes. Okay, it is definitely possible, which is kind of the whole idea of this question. Is it seems to be confusing, but if it is confusing, that means some people may not have a thorough understanding of bit pattern versus the interpretation of the bit pattern. Okay, so those two things are different. Is that okay? Okay, so before we even talk about that, okay, you guys can see a little bit of the blackboard, right? The chalkboard. Okay. So if I were to draw something here, you can say, oh, that's a blah blah blah, but that's your interpretation. What is actually on the chalkboard is what? Chalk, particles of chalk, right? So if you look at everything with a microscope, all you can see is chalk, which has no meaning. Definitely not the symbolic meaning that you think that you're seeing. Okay, so just to emphasize what I mean by that, I'm just going to do it over here just a little bit, just so that we understand what we mean by that. Okay? Okay? Let's make it 3 eyes. Here we go. Evolution, right? The movie. Okay. So when you look at this, you go like, oh, it's a happy face, but it's from Evolution, the movie. Okay. But that's only because you're interpreting the pattern that you're seeing. It's an interpretation. So if you just kind of imagine that you have a microscope and you're zooming in, zooming in, zooming in, zooming in, at some point all you can see are chalk particles, right? Little specks of chalk. And then if I ask you that question again and say, what are you seeing? What is the interpretation? You go like, I have no idea. There's no interpretation because all we are looking at are just tiny little chunks of chalk. Is that okay? So binary numbers are the same way. Binary numbers are nothing more than just zeros and ones, which boils down to the states of transistors. You have a whole bunch of transistors, some are on, some are off, and that's it. That is the state that is inside the computers, your cell phone and whatnot. What does it mean? Okay, this whole 8-bit pattern, let's say it's an 8-bit pattern. What does it mean? It may be a number. If it is a number, it may be signed, it may be unsigned, maybe it's just an ASCII code. Okay, so if I don't tell you how to interpret it, then there's no default interpretation of the bit pattern. They're nothing more than just a sequence of zeros and ones. All right? So with that out of the way, I'm just gonna work out this example here. Because the confusing part, or the seemingly confusing part of this particular question is borrow means that the minuend is less than the subtrahend if the borrow flag is set. But it seems like it's the same thing for the sign flag, okay? The sign flag is set if the minuend is less than the subtrahend. So it seems to be contradictory. How can one be set and the other one be cleared? Well, the reason why one can be set and the other one can be cleared is because the borrow flag is only making sense, or it's only meaning that the minuend is less than the subtrahend when you look at the values from the unsigned perspective, when you interpret the zeros and ones as unsigned values. The sign flag, on the other hand, is only making sense, or it only means that the minuend is less than the subtrahend when you look at the binary bit pattern as signed interpretation. The other one is unsigned, one is signed. So that is where the confusion may come from. So let me start this first. So are there any questions about that portion, to clarify the potential confusion about, okay, the borrow, the sign, how come one can be set, the other one can be cleared? Yep.
How would you prove or calculate that?
A calculator?
Is there a way to calculate like that it is possible or not possible?
Well, let's see whether this works. Okay, so I'm just waiting for my tablet to be connected, and everything is a little bit slow because I didn't drink coffee. Perception. I think I need to get a solid drive here for my computer, but I'm too cheap. Oh, it has a software update. Do not install now. Now would not be a good time to do it. Sorry? Oh, that's right. You cannot stop it. I wonder whose decision, kind of was that. I mean, it just doesn't make sense that you do not let people specify that I do not want to update now. See, if Skynet runs on Windows, I have nothing to be afraid of. Absolutely nothing. You just have to stand and watch. Don't you need to update now? Oh yeah, that's right. And it takes 6 reboots, right? Only to find out, you know, in the 7th reboot, that has to roll back everything. And then the hard drive died. All right, okay, so let's take a look at this particular case. So we are dealing with a case where the borrow flag has to be a 1, the sign flag has to be a 0, so we want to figure out, you know, how to generate a case like that. So if you have a question like this, you know, how do you start with this kind of question? You look at, well, one is you look at the definitions, right? You look at the definitions first. Okay, so the sign bit is the most significant bit of the difference. Okay, the borrow flag, on the other hand, is the most, this is basically bit 3, okay, borrow bit 3. And the way we do this is we say T3, we know the equation, don't we? Okay, so T3 is the negation of x2, the non-negative version of y2, or the negative version of q2, and the non-negative version of t2. Does that look familiar to you? Okay, that's one of the definitions. So when you look at this, you go like, okay, so we need T3 to be a 1, which means, you know, we need at least one of these two expressions to be a 1. But we also know that only up to one of those two conjunctions can be 1, so we can pick one. So let's say we pick the first one. In other words, we basically say, okay, let's say x2 is a 0. Oops, I keep clicking the stupid button on this stylus. So we say x2 is a 0, y2 is a 1. Okay, so can I come up with a case where, you know, 0 blah blah minus 1 blah blah, and I want the borrow flag is already guaranteed because of that, but I also want this to be a 1 here. How can I generate a case like that? Well, if I want the most significant bit of the difference to be a 1, I already know what Q1 is supposed to be, right? Or Q2, sorry. So Q2 is definitely going to be a 1 because 0 minus 1 has a result of a 1. We know that because Q, by definition, is the exclusive OR between the X and the Y. So now I just need to make sure that T2, which is the thing that goes into this place here, is a 0. Okay? I want that to be a 0. How can I guarantee that to be a 0? What about making all the least significant bits zeros? Doesn't that make sure that T2 is going to be a 0? So now just backfill everything. 0, 0, 0, 0. I have my case. I have my example of how to do a subtraction so that after the subtraction, the overall borrow is a 1, T3 is a 1, but we also want to make sure that the sign flag is...
You need to make sure the sign is 0. No?
Oh, we want the sign to be a 0. Okay. So excuse me, I got it a little backwards, but you can see how I reasoned it out, right? Okay, so I need to go back a little bit more like that because I want the sign flag to be a 0. Does that make any sense? But we also know that Q is going to be a 1, so I need this to be a 1 as well. So I need to have another borrow. How do I guarantee another borrow? What about this? Wouldn't that guarantee another borrow? Now the least significant bits or beyond that point, I don't really care, just throw some zeros. Is that making any sense? But you can see how I can step by step, you know, kind of use what I need to achieve to lock down, you know, some of the values first. And then I use the definitions of these bits, okay? T3 locks down this bit to be a 1. 0 minus 1 is a 1, so I need to generate this one to be a 1. But since this is also a borrowed bit, I just need to make sure that the earlier digit, or the one that is less significant, is a 0 minus 1, which guarantees that borrow to be 1. And that's how I generate my test case. Is that okay? Yep.
So you just arbitrarily said, okay, the borrow flag has to be set. So let's pick one of the combinations of x and y such that
Yeah.
the borrow flag is set, and then you just work from it from there.
Yep.
But you didn't actually know at that point whether or not it was true or false. Like the first question.
The first question. That is correct. So at that point, I did not know whether it would be true or false. Now, there's another perspective to answer this question. Okay, so the other perspective to answer the question is like this. B equals 1 means unsigned less than. Okay, the sign flag being a 0, assuming the overflow is also a 0, means signed not less than. Okay, so that gives me an idea as well, because what I'm looking at here is in one comparison we have less than, in the other comparison we do not have a less than. Now that is telling me something that's really important, because the positive numbers in signed interpretation are exactly the same as the unsigned interpretations. Okay, in the case of a 3-bit number, 0, 1, 2, 3, whether it is signed or unsigned are represented exactly the same way. 0, 0, 0 is 0, whether it's signed or unsigned. 0, 0, 1 is representing 1, whether it's signed or unsigned. So I definitely need to make use of some signed values in this case. So just in my mind, I'm going to say, okay, let's do a 0 minus. Okay, on this side, I'm using the unsigned interpretation. So I know that this number, the subtrahend, cannot be 0, 1, 2, or 3, because otherwise it will be the same result. I know it has to be something other than 0, 1, 2, or 3. So we can try 4, we can try 5. Okay, let's try 5. So 0 minus 5 unsigned is going to give me a borrow. But the other side, I want to look at the signed interpretation of 101 as a 3-bit signed integer. What is that going to be? If you kind of imagine a circle wheel, okay, what do you think 5 is corresponding to as a negative value? You can always count backwards, okay? You basically look at 0, and then if you take one position back, it's going to be -1, which is also known as 7, right? You take it another clock back, another position back, then you have 6, which is -2, and then you take another click, then you have 5, which is -3. So the bit pattern of -5 is also representing -3 in the signed interpretation. So in this case, you can see how 0 minus 5 is going to have a borrow, because there's no 5 in 0. Okay, so that's going to be guaranteeing a borrow flag here. But at the same time, 0 minus -3 should give you a 3, which has the sign flag being off. Yep.
Wouldn't -5 have the same bit pattern as 10?
But that's not the case with a 3-bit number. So with a 3-bit number, your circle is a little bit smaller than this 16, a 4-bit number. So you get 0. These are all the slots for a 3-bit number, right?
Oh, it only goes to negative. Oh, yeah, no, -4.
Yep, it does go up to -4, or go down to -4.
And you're saying if it went.
But -4 is also representing 4 in the unsigned interpretation. 5, 6, 7. There you go. So using this particular way of looking at things, then I say, okay, so if I know that 5 and -3 should work out, what kind of bit pattern are we looking at? So we are now looking at 101 as the subtrahend. So at this point, it's really just a matter of verification. You run it through and see if it works, and This does work. But I'm going to work this through just to make sure. Okay, 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. So here's my borrow flag, and here's my sign flag. We got the scenario that we need. So you can see how I approach it from two different angles. The first one in the previous page, it is strictly working out of the equations, the definitions of the borrow flag, the sign flag, the Q, the intermediate sum or difference flag, and so on and so forth. This one is based on the interpretation of, oh, the borrow is a 1 if and only if unsigned, it is unsigned less than. The sign flag, on the other hand, is a little bit more tricky because you have to make sure overflow is not overflowing, but that means you can choose values that is guaranteed not to overflow it. So is that okay so far? Yeah, okay. So getting back to the question, but does it help illustrate how to answer questions like this? Okay. All right, so getting back to the question here, moving on to question number, okay, question number 3 is very similar. I think for most people, they are exactly the same. So, huh? No, I just want to illustrate 3 because it's the same. So I'm not going to explain question number 3 because 3 and 1 are basically the same. Okay, what about the other way around? Okay, so let me just kind of flip this question around and say, what if I want the borrow flag to be cleared, but the sign flag to be set? How do I come up with a case like that? So let's try that one more time, okay? So this time I want the borrow flag to be a 0, but I want the sign flag to be a 1. Is that okay? So I want T3 to be a 0, and T3 is not x2, y2, or not q2, t2, and I want that to be a 0. B is basically D2, bit 2 of the difference, okay? So these are my constraints, and how do I play with these constraints to come up with a case to make this true? That is the question. So it's kind of the flip side of what we did earlier. So in order for T3 to be 0, I need not x2, y2 to be a 0, okay? I also need not q2, t2 to also be a 0. But I want D2 itself to be a 1. All right, so if D2 is a 1, that 1 has to come from somewhere. Where do you think it can come from?
X minus y. X2, y2.
Okay. So we need a borrow to be a 0, which means, okay, so this may work. Okay, so we'll give it a try. So let's say x is 1 and y is 0. In order for this to work, this is a 1 here already. We need this to be a 0 as well. In order for this to be a 1 and that to be a 0. So now the question is, how do I guarantee this particular 0 here? That becomes the only question. Well, that's pretty easy, because if all the least significant bits are 0s, then the borrow, that particular borrow that I have circled, is guaranteed to be a 0. So I just backfill everything with 0s, and I have my example. 100 minus 000 is going to have the borrow flag being a 0, but the sign flag is a 1. Is that okay? Now, since we're talking about flags, I'm going to jump around a little bit. I'm going to jump to the last question, because the last question is also related to flags, and it seems a little bit more complicated, but it's not, okay? There are 2 variations of question number 7. I think they are just kind of flipping the bits a little bit. So let's think about this one a little bit. after a binary subtraction, I'm just reading the question here. We know the following condition is not possible. In other words, don't even try to find a case to make this true because I'm telling you it is not possible. The borrow flag is a 0, the sign flag is a 1, but this time it is not possible because I also throw in the overflow. I tell you that overflow has to be a 1, and that makes it not possible. Explain why this is the case, why it is not possible, using definitions of the borrow, difference, overflow, and etc. In other words, I'm reminding you to go back to the definitions because the definitions will help you answer this question. And then I say hint. A state combination of 2 of the flags. In other words, when you look at 2 of the flags, it would imply the third flag, but the implied value contradicts what is given to you, okay, or what I think is impossible. And then, the last sentence, basically gives you the order. Think of the definitions of the overflow flag, the sign flag, and the borrow flag. Now, I didn't quite spell out, in this order, think of the flags, because I think, I think I got you enough clues already. So once again, let me copy the question first because I cannot remember. It's BSO is 011. Okay, BSO is 011. Okay, BSO 011. Okay. So I'm going to focus on the overflow flag first, okay? Because the overflow flag is one of the more restrictive flags. It touches on a lot of things, okay? And that's what we like about it. So the overflow flag, after a subtraction, is defined in the modules already to be minuend, negation of subtrahend, negation of the difference, or the negation of the minuend, non-negated subtrahend, and non-negated difference. And these are all the most significant bits. Okay, so we are only looking at the most significant bits of the minuend, subtrahend, and difference. Okay, I want that to be a 1. Don't you think that kind of locks down things quite a bit? Okay, so I can only have one or the other conjunction to be true. I can have this conjunction to the left to be true, I can have the conjunction to the right to be true. But in reality, I really don't have a choice because I also want the sign flag to be a 1. That's one of the requirements. So because the sign flag has to be a 1, okay, I'm going to draw this just so that graphically it shows. It points to this one is the only chance. That's my only chance of having the overflow flag being a 1 when the sign flag is a 1. Is that making a sense? Making sense? The symbols are kind of messy because this D is really the sign flag itself. Okay, this lowercase s is the most significant bit of the subtrahend, but this uppercase s is the actual sign flag of the difference. So that's why it looks a little bit kind of confusing, but it locks down that I only got one single conjunction that can be true. But that conjunction is really helpful because it locks down the most significant bits of everything. It tells me that the subtraction I'm dealing with has 0 for the most significant bit of the minuend. It has a 1 for the most significant bit of the subtrahend. It also has a 1 for the most significant bit of the difference. Don't you think I have all of this locked down already? But that's already enough. Because what is the borrow flag? What is T3? The negation of the most significant bit of the minuend and the non-negative version of the most significant bit of the subtrahend. I mean, in the notes I use XY, okay, but in this notation I already have those things as lowercase n and lowercase s. Might as well just put it here. Yep.
That formula is the one with like the or and then like x comma.
Well, that's the or stuff too, yes.
Well, is that where you're getting that from? Is what I'm asking. Is that where you're getting that from for T3?
Yes.
Okay.
So the or part is, is not even important here because I already know that this is a 1. So now we know that if we have the overflow flag being a 1 the sign flag being a 1 after subtraction, the borrow flag has to be a 1. There's no other way. That's it. That's the whole chain of reasoning. Yep.
Would there be like multiple ways to show this?
Yeah,
Maybe
possibly.
Potential flags that you could be contradicting, right?
Yep. You can use the borrow flag and the overflow flag to lock down the sign flag, I guess. Yep. So there are multiple ways to lock down and say, okay, by looking at these two flags, it implies the third flag cannot be the value that we want. So, but the idea is still the same. You go for the definitions of the flags. Is that okay? Does this sound like one of those logical games that you play? Well, it's not a game, but it is a logical problem. You're looking at the constraints, you look at what you know already, you look at all the clues that you already have, and then you start your deduction. Pretty sure Sherlock can get it done in like 20 seconds. But that's a fictional character. All right, so are we good with number 7 too? Because that's number 7. Now, since we're also talking about flags, we can now go back to the exclusive OR one, which is rather painful to some people because it's they missed it just by a little bit. It's this one. It's number 2. Okay, so question number 2. Okay, for those of you who forgot about, well, I guess it's not, because this one is carry, the other one is a borrow. So, but they're very similar, okay, because the only difference between the carry and the borrow is the negation. Okay, so in this particular case, I basically say, instead of using a regular OR to compute the carry flag at bit position I+1, can I use an exclusive OR instead? Okay, that's the question. Yes or no? Yes, we can, or no, we cannot. That's basically what the question is asking. And the answer is yes, okay? The new definition is gonna work just fine, okay? But then you remember the truth table, okay? So when we look at the truth table, we know that exclusive OR and OR are different because when you have A, B as independent variables, 0, 0, 0, 1, 1, 0, and 1, 1, A or B, okay, easy stuff, 0, 1, 1, 1, A exclusive OR B, and then if someone says, but I don't know what is exclusive OR, but the question itself defines exclusive OR right here. So exclusive OR is actually defined in the question itself. So if you apply that, it becomes 0, 1, 1, 0. Okay, so we have one row that is different. The last row here is saying, hey, if both of the expressions to the left and to the right of the operators are 1s, then OR is not the same as exclusive OR. So we kind of need to make sure this, we can either confirm this can happen, or we have to make sure that this does not happen when we try to compute the carry flag. Okay? Okay. So getting back to the definition of K I+1, it is xi, yi, or, well, I'm going to put a dotted line around the circle because we don't know whether we can or cannot use exclusive OR. And then we have qi, ki. Okay. So the key here is, what exactly is qi? Qi is not what we call an independent variable. It does depend on something that is already in the equation. What does it depend on? Xi, yi. Okay. So qi itself is xi exclusive OR yi. Okay. So now you look at this and go like, okay, so when xi yi is 1, okay, which means ki plus 1 is a 1, okay, can qi ki also be a 1? No, it cannot, because xi exclusive of yi, if both are 1s, then the exclusive OR is going to give you a 0. If you have 1, 0 already, it doesn't matter what ki is, okay, because the whole conjunction has to be false. Okay, fine. So this is only going in one direction. If xi yi is 1, then we know that qi ki cannot be a 1. We kind of have to go the opposite way and ask the question, what if qi ki is a 1? Does that imply xi yi cannot be a 1? Because you have to make sure that one cannot imply the other and go in both directions. Okay, so let's say qi ki is a 1. Now, why ki is a 1? Who cares? Because that's the less significant bit doing its thing. Okay, but if qi is a 1, what do we know about xi yi? We don't know which one is a 1 and which one is a 0, but we know they're different. Well, if you're dealing with binary digits and you know 2 digits are different, one has to be a 0, the other one has to be a 1, which means the conjunction of those two has to be a 0. So now we have proven that xi yi implies qi ki is a 0, qi ki is a 1 implies xi yi is also a 0, which also means that they cannot both be 1s. If they cannot both be 1s, then the last row of this truth table would never happen. If that last row does not happen, the other 3 rows are identical. So that means in this particular context, disjunction versus exclusive OR will work equally. So is that okay as an answer? Okay, cool. All right, so I've jumped around a little bit, but questions 1, 2, 3 are done at this point. And I just clicked on the wrong key. 1, 2, 3 is done. Number 4. Okay, number 4 is really just a matter of figuring out the meaning of the figuring out the value of the number. So I'm going to write it down here. 30.12. Okay. So you don't have to even use full equations. You can basically just say that this is corresponding to 1s, this is corresponding to 5s, 5s. This is corresponding, now this is the important part. This is corresponding to 1/5, and this is corresponding to 1/25. Okay? You can express these things as 5 to the power of 0, 1, -1, -2. You can express it like a fraction, like this. You can specify, this 1 is specifying the unit of 0.2, and this 2 is specifying the units of 0.04. It doesn't matter. If it boils down to the same thing, you still get a credit. Okay? So now you just have to do the multiplication. So we have 15 here, 0 here, 0.2 here, and then we have a 0.08 here. And when you add up all of these things, we have 15.28. Whoops! I clicked the button again. So that would be the answer. So is that okay? All right, cool. So that's base conversion. There are 3 versions of these questions, so depending on which one you get, your actual values will be different, but it will be the same way of solving the problem. Yep. Did I mess up my math?
I think 0.8 times 2.
0.04 times 2, right? Because we got 2 of those.
Oh, yep. Okay. Yep. Sorry, I was confused.
Okay. Yeah, I didn't specify multiplication.
Yeah.
Yep. I just need you to somehow show me that one specifies the quantity, the other one specifies the unit, what am I multiplying to, and then do the summation, and that's it. I don't think you need a calculator for this. You might feel more confident with a calculator, but ultimately you don't need one. Okay. So question number 5 is asking basically the reverse. What is the base 2 representation of a particular value that is already given to you in base 10? So in this case, it's 10.875. Okay, so let's take a look at 10.875. It's a base 10 number. So what I'm expecting is something like this. You just have to identify this whole thing as a summation of powers of 2. Okay, so we got a 0.5, we got a 0.25, and we also got a 0.125. Now you can specify these things as 0.5. You can also specify as 1/2, 1/4, 1/8. You can specify these things as 2 to the power of -1, 2 to the power of -2, 2 to the power of -3. They're all the same to me. Okay. But the next step is kind of important because now we still have base 10 numbers, right? So how do you convert it into base 2? So you can either specify that the 8 specify a 1 followed by 3 zeros, the 2 specify 1 followed by 1 0, and so on, or you can do it like this. So that's how I would do it. So you basically just convert each power of 2 into the equivalent base 2 representation. Because now, because they are all occupying different positions, so the addition of these digits will be the same as adding any base. Doesn't really matter. So we have 1 0 1 0 in this case, 0.111, the whole thing in base 2. So something along this line. If I see just the final answer, that may not get any points because it is the steps that matters. If I see somebody making a stupid mistake somewhere, like not remember this is a 1 0, but instead put a 0 1 over here, that person will still get close to perfect score. Yep.
What about, so for number 2, how we were doing the truth table for or exclusive or? What if somebody went through and showed all that, but couldn't show that the 1 1 never happens? Do they get no points for that, or do they get points?
They get partial credit.
Okay.
They get partial credit for showing that OR and exclusive OR are different and how they're different. So they will get partial credit for that. But the more critical part of the question is the understanding that Q relies on XY. So if XY are both 1s, then Q has to be a 0. That is actually the most crucial part of the question. So partial credit, yes, but definitely not full credit. Okay, so is this okay? The conversion to binary number? Okay, all right. And I think we're only left with question number 6 then. Okay, question number 6 is a trick question. Wasn't really intended as such. It's more intended as a free question. It's like, oh, it is so easy. Just get those points first. Okay, so the question reads, assume we can use gates of any number of inputs. In other words, unlike in the previous or the practice exam where I lock down and say, oh, you can only use gates of 2 inputs, I'm now allowing you to use gates of 60 inputs if you need to, okay? And assume all gates have the same propagational delay, okay? So they all have the same propagational delay, okay? No difference between OR and an exclusive OR gates. No difference between, no dependency of the fan in either, okay? You can have a gate that has 60 inputs versus a gate that only has 2 inputs, same propagational delay, okay? No difference whatsoever. If we know that a 3-bit carry look-ahead adder, which you already know, takes 3 nanoseconds to finish computing the sum and the overall carry bit, okay? So in 3 nanoseconds, we get everything that we need out of that particular 3-bit adder. How long does it take for a 6-bit carry look-ahead adder to complete its computation? Explain your answer. So the answer is 3 nanoseconds in this case, because that is the whole point of the carry look-ahead mechanism. How do we explain that? Well, you have to explain it in the form of the level of gates does not change. Now, what changes would be the number of gates, right? When you get to like 6 bits, one of the borrow bit, the last borrow bit, is going to have a lot of AND gates, combining into the single OR gate, okay? But that part does not matter because the number of levels that you have to go through is still the same. 4 levels, the same. It doesn't change. That part does not change at all. So this one is kind of difficult to give partial credit. Yeah.
What if you just say that like the time it takes for each carry and a carry look ahead doesn't change? Like no matter how many carries you have.
But why?
Because that's the whole point of doing the carry look ahead.
I suppose that's going to be okay. I'll kind of go easy on this one.
I guess for this one, like the only time it would be different is when the bits are like it's 1 bits instead of 3 bits, it's 1 bit because then that would just be one of the gates.
True. If it is a 1-bit adder, then you may not need all 3 levels of gates. I mean all 4 levels of gates. Yep. And that's why I chose 3 and 6 because I know 3 needs all the levels already, and 6 definitely needs the same number of levels.
Well, right? 2 needs 4, right?
2 still need the same levels. Yes.
Yeah.
Yep.
Just the one that-
Yep. So is that okay? No, for number 6? Okay. Because that's the whole point of having carry look ahead mechanism. All right. So that kind of explains the whole all 7 questions. This is the first time I actually have 7 questions in the exam. Usually I get like 5 or 6. 5 usually. But having 7 questions is nice in the way that you can have 1 question answered incorrectly entirely, and it doesn't have as much impact to your overall grade. Second thing is, do you guys remember what is the percentage that you need to get a C, or the equivalence of a C, just for this particular test? 37.5%, which is 3/8 to get a C. It is 0.11 times 2 to the power of -3. Correct. Or 0.011 in base 2. Sorry? What?
How many questions?
We have 7 questions. I definitely make it a very odd number.
No, he doesn't. How much questions do you get right to get a C?
Like, let's say if we were to break it down to 100.
You still need 3, okay? Assuming your answers are either entirely correct or entirely wrong, you need 3 in order to get a C. 3 out of 7. But if you get partial credit, you might have like 2.
I mean, like as far as either a whole or nothing. If
Oh, okay.
break it down that way.
Okay. So are we okay so far with the exam? Yep.
The exam is going to be even number of points, so like each question is 1/7.
I'll let Canvas do all the scaling.
Okay.
For each question, yes, all the questions would have the same number of points, but when it combines into the exam, quote-unquote exam itself, then Canvas would just say, okay, all of these things will add up to 20% of your final grade, and it will do all the scaling. Yep. Okay, so are we okay so far with the exam? Exam is done, okay? All right. So that means we can now move on and get back to memory devices, which is the topic that we kind of talked about before the exam, and we were halfway through. And my computer is being extremely slow. Okay. So that was from this particular module, D flip-flop and other basic memory devices. And last time we talked about the D flip-flop already. We were just about to talk about the edge-sensitive D flip-flop. So I don't know how many of you read the notes like prior to the class, at least a little bit, touch on it a little bit. It definitely helps because your mind will be kind of primed if you read the notes a little bit ahead of time. So we are talking about section 5, Okay, section 4 is done already. Section 5, starts the discussion of an edge sensitive D flip-flop. And I use the hardware description language or object-oriented hardware description language to describe how the gates are connected. So how many of you are able to reconstruct this just from the text representation? Okay. You should be able to, okay, if you try to do it, you should be able to kind of put the circuit back together just by reading the text. Yep.
Do you expect something of that nature to be on the second exam, or do you give us something raw?
You're gonna hate my answer. I have not decided yet. If I'm too lazy to draw the picture, because if I use the picture, I have to kind of do the drawing in Logisim, export the PNG and then import it back into the exam. This I just type. No, I think I'll just give you the diagram because I don't want you to spend extra time in the exam to read all this. Okay, that is not the point of this class. Okay, so with this one, yep.
I was just curious, how close to an actual hardware description language is that?
I have no idea. I know this is very object-oriented. I would assume the syntax would not be the same. I would assume the object-oriented portion would not be the same. Like they're not going to use new. They would not use classes like your usual C++ class. But I would assume that they would use, but it will still be text-based. In other words, there will still be identifications of different ports of a particular component, and there will be a way to specify that these things, all of these ports belonging to possibly different components, are connected to the same electrical node. So there will be an equivalent way of representing it, but how it is represented, I'm not sure. It's going to be simpler than this. I don't think it's going to be any more complicated. Okay, so getting back to this one, I actually got the circuit done already, and I put it into the shared folder, so you guys can download it and play with it. So if you go to the share folder, which there's a link at the beginning of the first module. So if you go to circuits, I just put it in today. mem.circ, is the one. So if you download that one, so let me download it here. Okay. So let's see, where's my download link? Right click, download, there we go. Okay. And I'm going to save the file to my temp folder. Okay. And start up Logisim. Open the file in the temp folder. Okay, so that's your usual SR latch. I'm hoping that you guys still remember the basic SR latch. S for set, R for reset. Okay, so basically it has a slash in front of it because it is active low, which means if it is a 0, you are specifying that action. If it's a 1, you're basically saying, no, I'm not specifying any action. So the other circuit is done here already. And let me zoom out a little bit just so they can see the entire circuit. The E, the error bit, is going to be there when you load it. It's okay. So you basically have to run it a few times to reset it. Or I suppose we can reset simulation. Nope, that didn't save it. Disable first. Reset, and then re-enable. Yeah, it doesn't like it because the pins are having the same state they're changing states at the same time. See how these two are ones at the same time? So they're turning from 0 to 1 at exactly the same moment, and that's why we have a quote-unquote oscillation because of that. We looked into that oscillation issue before, remember? And it is just that, just like it's because of that. So the way to change that is really just to give it a 1 and then change the state. Okay, so now it is safe. Okay, so let's change it back to a 0. Now you can see that when clock is low, okay, I can flip the data bit as many times as I want. It doesn't do a single thing to the output. This is the only output. Okay, just Q. There's no not Q. Okay, so if I want to change the output to a state of 0, you can say, oh, maybe the clock here will make it happen, right? Indeed, when your clock goes from 0 to 1, whatever is presented to the D pin, which is an input pin, is reflected to the Q, which is an output pin. But guess what? At this point, even though clock is still a 1, I can flip D as many times as I want. It doesn't change the output at all. If I want to change the output from a 0 back to a 1, I have to specify a 1 with D, and then the clock going from 1 to 0 doesn't do anything either. It is only when the clock goes from 0 to 1 that the D pin is going to change the C SR latch, or the SR latch that is labeled C over here. So this is what we call an edge sensitive D flip flop, which means when the clock line, the CLK line, is going from a 0 to 1, only at that particular moment, the circuit is going to sample the D pin, and then whatever it samples at D pin at that exact moment is going to be stored into the C SR latch that I call C over here. After that moment, you can change anything you want. You can change D, well, not anything, but you can change D any way you want. But you can also change clock to go from 1 back to 0, and that will not do a single thing to the state of the entire thing. In other words, we have gone from a level sensitive D flip-flop to an edge sensitive D flip-flop. The question is, when do we sample the input to change the state of the memory device? That is the question. With a level sensitive design, as long as the enable line is a 1, the state of the memory device is affected by the D pin. With an edge-sensitive design, it is only sampling when the clock is going from 0 to 1. So that is the big difference. So are we okay so far? Do we understand the main difference between the two designs? The details is really horrendous. Okay, so the analysis of this circuit is a little bit hairy, but it is presented nonetheless. Okay, so I have done the analysis and presented over here. Okay, so the analysis is broken up into multiple sections. The first section talks about what if the data bit is a 0 or D pin is a 0, and we are looking at a rising edge clock. Okay, rising edge means the clock is going from 0 to 1. So when D is 0 and the clock pin is a 0, then what's going to happen? Okay, so if we go back to the circuit diagram, where's Logisim? There we go. Okay, and zoom in just a little bit more. Okay, and scroll up a little bit, like so. There we go. Okay, so at this point, this is exactly what my notes is trying to capture, is what if D is a 0 and clock is a 0? Well, if D is a 0, it guarantees the N2 is going to output a 1, right? Because it's a NAND gate. With a NAND gate, if at least one input is a 0, the output is going to be a 1. So we know this is going to be a 1, which means it is not going to set the SR latch that I just called S over here. If clock is a 0, it's going to do the same thing to the other NAND gate. Now this NAND gate has 3 inputs, not 2. But it's going to do the same thing, because when clock is 0, N1 is guaranteeing to output a 1, which means /R of the C SR latch is also guaranteed to be a 1. Is that okay? and I'm just tracking down the wiring and see if anything else I can know for sure. Okay, there's one more thing I know for sure. The clock line is also directly connected to the /R of the SR latch. Okay, and because of that, when the clock line is a low, we also know that the SR latch is guaranteed to output a 0. But you can see that I don't even care about Q in this case. I only care about /Q or the negation of Q. But because Q is reset, that means the negation of Q is going to be set or be a 1. And that goes back into the N1 gate. But it really doesn't matter because N1 has one input being a 0 already. Yep.
So Q is still set because we're not needing it to reset because /R is active low, right?
Say that one more time.
Q is still 1 because on
Q is not, which Q?
the very bottom.
Oh, the actual output pin Q? Yes. So this is from the previous state. We haven't done a single thing yet.
And we haven't specified a reset because it's active low, right?
That is true.
Okay.
So this Q being a 1 is basically what it has already memorized from before. Because when you look at the input to the CSR latch, both inputs are 1s, and they're guaranteed 1s too. Because one comes from N1, where it is guaranteed a 1 because the clock is a 0. The other one comes from /Q, but /Q is guaranteed to be a 1 as well because /R of the SR latch is getting a direct input from clock, and clock is 0. So that's why when clock is 0, we guarantee that Q is not going to change. Okay. So from this, we change the clock from a 0 to a 1. So this is where the magic happens. Okay, this is the transition that updates the output clock. But before I click it, okay, let's think about what's going to happen. Okay, and this is, I encourage all of you to read the notes, and study in this class the same way. Okay, you could just click it and watch it happen, but that's not going to help you understand the material. Okay, so instead of just clicking and observe what is going to happen, use your mind to project what is going to happen, to model this whole thing. Okay, because that is what this class or most computer science or math classes are about. So the moment I click on the clock pin, it's going to transition from 0 to 1. Now what is that going to do to the entire circuitry? That is the question. So we're going to go step by step. Okay, we will look at what clock is directly connected to. Clock is directly connected to here. That's not going to do much, right? Because that's just going to change /R from a 0 to a 1, which means this SR latch is going to have both inputs being 1s, and it will just kind of maintain the output to be a 1. So nothing is going to happen much to this guy. Let's think about something else that is connected to. Oh, it's also connected to N1. And N1 right now is outputting a 1 only because clock is 0. So when we change clock from 0 to 1, it will change the output of N1. N1 will be affected. So when all inputs of a NAND gates are 1s, the output is going to be a 0. So now we track down N1 and say, what are you going to affect? N1, first of all, is going to affect the CSR latch, which means it is going to assert the reset pin, because a low to the reset means it is resetting. So that means Q is going to be a 0. But that's not the only thing it connects to. N1 also connects to N2. But N2 is not going to change its output because N2 is also getting a 0 directly from the data pin, which means N2 will continue to output a 1 even after clock goes from 0 to 1. So that is my projection, okay, just based on looking at a circuit and figuring out which input is going where and how that is going to propagate the change. My conclusion is the CSR latch is going to change its output state from a 0 to a 1. This will be asserted, okay, but the rest of the circuit would not be affected. This input will become a 1, which doesn't really change the output of the SR latch. So are we okay so far with that analysis? Okay, so we clock it, and that's exactly what happened. But now the question is, if I change D at this point, would it affect anything? Okay, if I click on this D here, would it change anything? And if it's not going to change anything, why is it not going to change anything? Because of the NAND gate, okay? Because D only connects to the NAND gate, but the NAND gate has one output, one input that is a 0 already. So D has no impact to N2 whatsoever. So whatever the N2 connects to is not going to be impacted when I change D from 0 to 1 and vice versa. Is that okay? All right, so just to illustrate, see, it's not going to change anything. It didn't change anything beyond N2. Okay, cool. What about clock? Okay, so let me change D from 0 to 1, and then we're going to say, okay, what if I click on clock so it goes from 1 back to 0? Okay, is that going to trigger any changes that we should know about? Well, it will trigger some changes for sure. Okay, because when clock goes from 1 back to 0, N1 is going to change its output, right? It's going to change its output to a 1, which means the CSR latch will now have both inputs being 1s. What does that mean? It means don't do a single thing, go idle, do nothing, right? Okay, so that means the output is not going to change. But we also want to track down the other line. It's going to go into N2. What is that going to do to N2? So N2 will now have both inputs being 1s because I flipped the data pin from 0 to 1 already. So N2 is going to output a 0. When N2 outputs a 0, it's going to assert this pin here, okay, which means the SR latch is going to be set, which also means /Q is going to be a 0. /Q being a 0 is propagated back to here, but this is going to be, it's going to set the pin. Hold on a second here. It's going to set the pin. Did I miss something? We know that's going to be a 1 when clock goes to 0. Huh?
Is it also going to turn it off at the same time?
Is it going to go through just one NAND gate, N1, or is it going to go first, or is it going to go through N2 and then S? Like, does the propagational delay affect?
There'll be propagational delay, but it should not oscillate. There's no oscillation in this circuit. So let me think about this one more time. Okay, we're changing the clock pin from a 1 back to 0. Okay, so the 0 goes here, N1 will become a 1. So that's not going to change the CSR latch. It goes back here, and then N2 is going to have both inputs being 1s, so it's going to output a 0. That 0 goes here. It is asserting the set, which means Q is going to be a 1, not Q is going to be a 0. Not Q being a 0 goes into here, which means we're going to set the circuit, which also means Q is going to be a 1.
But isn't /R also going to be 0 at the same time?
No, /R is 1.
/R is going to be a 1 because of
No, at S.
Huh?
Is the /R at S going to be a 0?
Yeah, because it's directly connecting to the clock.
Slash. Okay,
Oh,
wait.
You're saying that all the inputs to N1 are going to be negated?
We only
No, not to N1, to S.
okay
Yeah, to S.
Yeah, I know.
to S. This guy?
Yeah, that guy. So the /R, since the clock is 0, is also going to be 0, right?
And then /S.
So that's going to be a 0. Oh, right. So it's 0, 0,
Yeah.
which means both outputs would be 1s. So Q will continue to be a 1.
Yeah.
Okay, right. Okay, I forgot about that one.
So no change.
So no change to actual output state. So let's confirm that. Yep, no change at all. Okay, good. Because I missed that one connection. The connection that I missed was this connection here, going from clock all the way to /R of the SSR latch. Yep. So that's kind of cool. Okay. In the previous semester, somebody asked me, who came up with this stuff? And I could not answer that question. But whoever came up with this stuff, you know, really knew what he or she was doing. Because this is pretty ingenious. Because you basically have a state lockdown already, and any transitions at this point is not going to do a single thing. So figuring out, I mean, we are really just looking at a circuit done already and just try to mentally anticipate what's going to happen when we click on the pin. That's relatively easy compared to out of nowhere coming up with the design with this kind of behavior. So this is really cool. So going back to the notes, the other one is, what if the data pin is a 1 and we have a rising edge clock, and clock is a steady state, and why when the clock is a 0 or 1, you can flip the data pin all you want and nothing happens. Okay, so the reasoning is kind of broken up into different cases, like when the clock pin is a 1 and you change the data pin to a 0, why would that would have no impact? If the clock is a 1 and the data pin turns into a 1, why would that would have no impact, and so on. So every single case is kind of analyzed in this case in a particular sequence. So I'm hoping that you guys would actually spend some time. If you don't read this, it's okay. Go through the circuitry yourself in Logisim and think it through. That's just as good. Okay? So section 6, at section 6, I gave up on the text representation of the circuit. Yep.
I just wanted to know, what if you wanted it to trigger on the falling edge instead of the rising edge to set Q with alternate?
Well, you can always go for the cheap solution of negating the clock. Because that would just change the polarity of which edge is going to trigger the action. But if you want to look into making tweaks to the NAND gates and stuff like that, that I do not know yet. I don't have a ready answer for that. Okay, so number 6 is clocked and gated. Okay, so now we have 3 input pins just to store one single bit. There are 3 input pins because one is data, which is basically what am I storing? Am I storing a 0 or am I storing a 1? So data is always specifying what you're storing. Enable is level sensitive, okay? In other words, if enable is a 0, we're not going to do a single thing. Even if the clock line is flipping up and down all day long, if enable is a 0, we're not paying attention. Clock line is saying if enable is a 1 and clock has a rising edge, and only at that point we're going to store something to the last SR latch. So that's why it is combining both elements. It's combining the effect of a level sensitive D flip-flop as well as an edge sensitive D flip-flop. So the reason why we have the combination of these two is because a lot of times when we design circuits, especially inside the processor, we have one single line that is multi-dropped. In other words, one single conductor is connected to multiple D flip-flops. So when we specify a 1 and there's a clock, there's only one clock, okay? So clock is universal in the entire processor. There's only one clock signal to everything in the entire processor. Okay, so you kind of have to keep that in mind. This is a universal signal. This one is unique to every device. This one, a lot of times, is also a multi-drop configuration. So now the question is, we have a 1 on the data line, but it's connected to multiple D flip-flops. Who is supposed to store that 1? Who's supposed to change? The enable specifies who's going to change. The clock specifies when it is going to change. So if you want to update, or if you want to kind of leave a note on this diagram, clock is specifying when, enable specifies who, and then data specifies what. This is the first time I actually came to this realization to use those terms to explain the pins. That's why it's not reflected here yet. Is that okay?
Can you repeat that?
I'll do better.
Just real quick, what you just said. Repeat it one more time.
I'm going to do better. This is the INTP obsession thing. Okay. Oh, my battery is fully charged. And this is which one? 0298. Okay. All right, so I'm just going to put some notes here. Okay. CLK is when. EN is who. And data is what. Okay, got to be consistent here. There we go. Okay, so I just took note for you.
It feels like that should be like the other way around. Like, I mean, as far as between enable and clock, I feel like maybe clock says, or enable says when, right?
Nope. Enable specifies whom.
Like
It's specific to a device, right?
Huh?
Because it's specific to a device.
Yep, because every device has its own enable. But there's only one single universal clock of the entire system. In other words, you can kind of look at this as a class setting, okay? The D line connects to everybody. You guys are all listening to me at the same time. I don't see anyone putting on a headphone right now, so you're all listening to me, right? Okay. So that's what the data is, okay? The clock line is kind of like a universal clock in the classroom, okay? I'm just telling you, when you see this clock or when you see this thing going from this to this, you'll write down whatever I'm specifying, okay? So if I don't specify an enable, then the entire class is going to take the same note all at the same time, which is not what I want, okay? Because inside the processor, a lot of times you just need one single device to pay attention to the clock, to the data line at one particular moment, and then the next moment you want somebody else to pay attention. So I'm basically pointing to each person, okay? That's the enable, and say, okay, you pay attention in the next clock. Write down what is on the board, but only you should do that. The rest of the class should ignore everything. So that's why the EN specifies who is doing it, the clock is specifying when to do it, and then the data is specifying what are we remembering. Is that okay? All right. We are pretty close to the end of this, okay? And then one last one. You can see I'm building a bigger and bigger and bigger D flip-flop. So this one has a longer name. This one has a name of, it's a resettable, gated, edge-sensitive D flip-flop. Okay, so the only difference between this one and the previous one is it's resettable. In other words, you can see there's an extra pin here called reset. So what do you think it does? Why do we need a reset pin here? What happens when you first turn on the computer? What do you think is going to happen? What would be the states of all the transistors? They're not necessarily off. They're all wiggly and all over the place. Yep.
Does it just depend on like how fast a charge gets to each one?
Yes, then you have a raised condition because some transistors, just for whatever reason, has a smaller size, so it changes faster. Other transistors are, they're not changing as fast. Some have a shorter path, some have a longer path, and the path itself has inductance, and the inductance is going to change the timing just enough that you have no idea who's going to be a 1, who's going to be 0 when you first turn on the computer. So that's why we need a reset pin. The reset pin basically is also a universal signal to every single component. When the reset pin is asserted, it's telling everybody to go back to your default state, okay, which usually is a 0, but occasionally it is not. So when you turn on your computer, like a PC or your cell phone or anything that is electronic, the reset pin, so now the big question is, so who's controlling the reset pin, right? The reset pin controls everything in your computer, but who's controlling the reset pin? The reset pin is usually controlled by its own dedicated specific chip on a circuit board, okay? And that thing basically monitors the incoming voltage coming from your power supply, And it basically has two functions. One, it waits for that voltage to reach a healthy level, and that's usually programmable. Once it gets to the healthy level, it will assert the reset pin to tell everybody else to say, don't do a single thing, go back to your default state. And in fact, it will hold the reset line for a certain amount of time. To us, it is not going to be a very long time. It's usually in hundreds of milliseconds, which means it's a fraction of a second. But to the computer, it's a really, really long time. And that guarantees that every single device has enough time to go back to the default state. We are not just talking about all the registers in the processor. We're not talking about just the chipsets that you have on the motherboard. We are also talking about the PCI, everything that hangs off of the PCI bus, everything that hangs off of your USB bus, and so on and so forth. They're all supposed to reset to a known reset state when you first power up a computer. Okay? Yep.
So that's to avoid oscillation then?
No, it is to avoid anything that is unpredictable. Now, I'm not sure about you, but I have got into situations where my Wi-Fi, I think it was a Wi-Fi card, it would not work correctly even after a warm reboot, which is supposed to trigger the power, the reset line. It would not correct itself. I had to turn off the computer. In this case, it's a laptop computer. I had to turn it off, remove the battery, wait a little bit, put the battery back on, turn it back on, then it resets its state. So that tells me that somebody did not pay attention to the reset line. The reset line is interesting in many other ways too. Have you guys heard of a Watchdog Timer?
Yes.
Okay, what is a Watchdog
I
Timer?
have no idea, but they're a pain in the butt when your Windows install does not have the proper drivers for them.
Okay.
And it causes blue screens every 2 minutes. You know.
Well, consider yourself lucky if you see the blue screen, okay? Without the Watchdog Timer, you would not even see the blue screen, okay? So the Watchdog Timer works like this, okay? It's also kind of like a dead man switch, okay? So the Watchdog Timer has an internal timing mechanism, okay? And it requires, quote unquote, getting hit, okay, every so often. If it doesn't get, quote unquote, hit, doesn't get reset within a certain amount of time, it will assert the reset line and just say, it basically tells the whole system, it's like something is really wrong. I think we are in a really bad situation, but it's not a reset, it asserts what we call an NMI, a non-maskable interrupt, which means the processor has no way of ignoring that. Okay, so the Watchdog Timer is pre-programmed to reset to cause a NMI after 30 seconds of no one poking it. So normally Windows, has a timer, running in the background, and in software it is going to hit or probe the Watchdog Timer every so often, okay, to make sure that it doesn't go off. But when Windows is locked up for whatever reason, the Watchdog Timer doesn't get poked, so the timer expires, it goes off, the NMI, the non-maskable interrupt happens, and then that's how we got into the blue screen. Without the Watchdog Timer and without the NMI mechanism, you won't even get into the blue screen, which means there's no way to diagnose the problem whatsoever because your system continues to be locked up. The blue screen allows developers to have a chance to dump the entire memory content of the computer, of RAM, and also dump the states of all the devices, so there's a chance of debugging and figuring out why it is getting into the blue screen. So it is not annoying, it is actually helpful.
Well, it's annoying when Windows doesn't include the drivers.
Your cell phones have the same mechanisms too. In case you haven't noticed, when your cell phone is quote unquote locked up, it takes maybe 30 seconds or so, but then it will reset itself. And it's the same mechanism. Your cell phone has a Watchdog Timer exactly doing the same thing. But I was incorrect that the Watchdog Timer in a PC is not connected to the reset line, it's connected to the NMI, or the non-maskable interrupt line. In other devices, the Watchdog Timer does connect to the reset line, so after 30 seconds of no one hitting the watchdog, it just the whole thing. Let's start from the beginning. It reboots the machine automatically. That is much more practical on a Mars rover, right? Because with a Mars rover, what good does it do when you get into the blue screen of death? You're on Mars. Who's going to go there to do a memory dump and figure out what has gone wrong? You don't, right? So you just reset the whole thing, reboot from the beginning, and hopefully it will, avoid that problem for a while. Okay, and that's your best hope. All right. So I think we're done for today. This particular module doesn't have a whole lot more. Okay, so we are ready to move on to the next one in the next class, and then very soon we'll start to get into the processor stuff. So I'll see the late lab people at the lab. It's a continuation of your project, so if you're all done already, you don't have to show up.
So I was curious, we have a way to set up numeric codes to enable where to